Proportions in triangles. The side splitter theorem states that a line divides two sides of a triangle proportionally if and only if it is parallel to the third side. So again, reviewing our logic, this is a biconditional statement which makes the conditional and the converse true. So in the conditional, if TU and QS are parallel, then we can say that RT over TQ is proportional to RU over US. The converse states that if you're given a triangle that has this additional segment and you find that the length RT over TQ is proportional to RU over US, then you can conclude that these two lines, TU and QS, are parallel. So make sure you know the difference between the conditional, which gives you the lines parallel, then you can say the sides are proportional, versus the converse, which gives you side lengths, and if they're proportional, you can say that the lines are parallel. Here we need to determine whether the statement is true or false and explain the reasoning. So we want to see if these side lengths are proportional. So let's see if the ones across the top are the corresponding sides and the ones across the bottom are the corresponding sides. So this one talks about DB over the segment BA, and then it has segment EC over the segment CA. Now these are the corresponding sides. It follows the side splitter theorem. So our conclusion is that this is true using the side splitter theorem. So in the second example, again, we want to see if the segments on the top are corresponding and the segments on the bottom are corresponding. So on the top we have AC over CE, and then we have segment BC over DE. Now these are not the corresponding sides that we're supposed to use with our side splitter theorem. So we're going to say that this statement is false. In these examples, we want to find the value of each variable. So because we're given that these two lines are parallel, we can use the side splitter theorem that says that if we put 5 over the top part 10, that's going to be proportional to x over the top part on this side, 7. So then we can go ahead and cross multiply to solve. 5 times 7 is 35. 10 times x is 10x. And then lastly, we just need to divide by 10. So then we get x is equal to 3.5. Let's go ahead and work out the second one. Now in the second one, we need to be a little bit careful over here because 50 is the length of the entire segment on this side. So this x is going to correspond with 20, so we can put x on the top and it corresponds to 20 on the other side. But if we use this 50, then we need it to correspond to the whole length on this side, which is going to be 25 plus 20, and that gives us 45. So remember, you always need to make sure that you have the corresponding side lengths. If you put the short part over the whole thing, you need to put the short part over the whole thing. So now we can go ahead and cross multiply to solve for x. We get 45x is equal to 1,000. And then when you divide by 45 on both sides, you get x is equal to 22.2 for our answer. Here we need to determine whether the given information implies that segment BC is parallel to segment DE. So we're actually using the converse of the side splitter theorem. So if the side lengths are proportional, then we can say that the two lines are parallel. So let's go ahead and set it up. If we put 7 over 2, that corresponds to 8 over 3. And then to test, we're going to cross multiply and see if we get the same number on both sides. 7 times 3 is 21. 2 times 8 is 16. Now, because 21 does not equal 16, we can say that segment BC is not parallel to segment DE. So let's go ahead and check the second one. If we put 6 over 9, that corresponds to 4 over 6. And again, we'll cross multiply. 6 times 6 is 36. 9 times 4 is 36. And because this is true, that the sides are proportional, we can conclude that BC is parallel to DE. Here's a corollary to the side splitter theorem. And a corollary is really just an added note to an already existing theorem that we're just altering a little bit. So if 3 parallel lines intersect 2 transversals, then they divide the transversals proportionally. So instead of having a triangle that gets split by a segment, it kind of gets split by 2, and we don't really see that tip of the triangle. But it's still proportional in the same way. There are 2 ways we can set up these proportions. UW over WY is proportional to VX over XZ, or the other way you could write it is UW over VX is equal to WY over XZ. So here we want to use the figure to complete the proportions. We are going to use the corollary to the side splitter theorem, but I also want you to see something else in these diagrams. There is a small triangle, ABC, a medium triangle, ADE, and a large triangle, AFG. So make sure you're able to see all of that. So let's find the corresponding sides. We have segment AB over segment AF, and then corresponding with AB is BC. So I want you to see this carefully. We have across the top, we have the top side of the small triangle and the right side of the small triangle, and so across the bottom that needs to correspond to the top side of the big triangle and the right side of the big triangle. So the missing segment length in the proportion is going to be segment FG. And we're going to follow that same idea with the second one. Segment length AB, and then the other one is blank, and on the bottom we have DF compared to EG. So if you look carefully on this one, the purple one's across the bottom. It's just that extension from the second to third triangle and just this extension from the second to third. So to match that, we need to have, if we have that short part of the first triangle on the top, we need to have that part of the small triangle on the bottom. So the segment length to complete the proportion is segment length AC. Now we'll do this last one. Segment AD compared with AE, and then we have BD along the bottom, and that needs to match with just this extension. So make sure that it's always corresponding. So the missing proportion will have segment length CE. In these 2 examples, we want to find the value of the variable and using that corollary to the side splitter theorem. So I'll show you one method over here. If we put x over 10, that's proportional to 6 over 8. And then we'll cross multiply. You get 8x is equal to 60. And then we divide both sides by 8. And we have x is equal to 7.5. In the second example, we know that the lines are parallel because all the corresponding angles are congruent. So by the corresponding angles postulate converse, we can say that the 3 lines are parallel. And now we can use the corollary to the side splitter theorem. So this one I'm just going to set up in the other proportion. If we put x over 3, that corresponds to 9 over 3.5. And then we can cross multiply and solve. So we get 3.5 times x is equal to 27. And if we divide both sides by 3.5, then we'll get x is equal to 7.71, rounded to 2 decimal places. Now this is the last theorem we're going to talk about today. It's the triangle angle bisector theorem, and it states that if a ray bisects an angle of a triangle, then it divides the opposite sides into segments whose lengths are proportional to the lengths of the other 2 sides. Now I need you to pay careful attention to this one. This ray CD is an angle bisector, which means it cuts the angle ACB in half. So this angle C gets bisected into two smaller congruent angles. But this side, AB, it gets cut into two different segments, but those segments are not necessarily congruent. So you can't say that AD is equal to DB. So be really careful with that. But what we can do is we can set up a proportion with these four different segment lengths that we have now. So there are two ways that we can set it up. The first one, AD, the top part that gets cut off, over DB, the other part that gets cut off, equal to the side that matches with AD over the side that matches with DB. The other way we can do this is if you put AD over AC equal to DB over BC. Use whichever one you feel like you'll remember better. So here we need to find the value of the variable. So I'm going to go ahead and just kind of define that angle bisector, because this is what's going to split the triangle into the four different segments. So this first one, I'm going to set it up with these two segments. If I put the far side 3 over this side A, that corresponds to the far side 4 over this side 6. And then we can cross multiply and solve, so we get 4A is equal to 18. And when you divide by 4 on both sides, we get A is equal to 4.5. Now with the second one, I need you to be careful, because here is the angle bisector that cuts the triangle into the two parts, but we're missing the measurement for this segment CD. So we need to find a way to represent that. If this whole length is 7 and this part's x, if we knew what x was, we could subtract it from 7 and CD would be what's left. So we're going to take that idea and write an expression. So here we're going to put 7 minus x is going to be the length of CD. And then we're going to use that to set up our proportion. So this one I'll set up in the other way that I showed you in the theorem. So the two parts that get cut off, x over 7 minus x, is equal to this side 5 over 8. And remember, expressions always need to be in parentheses before we cross multiply, because once you get 8x equal to 5 times 7 minus x, we're going to need to distribute this side. So we have 8x is equal to 5 times 7 is 35, 5 times negative x is negative 5x, and then we need to get the x's on one side together, so let's add 5x to both sides, and then we get 13x is equal to 35. So when we divide both sides by 13, we get x is equal to 2.69. And that's our final answer. So that's it for this set of notes. I'll see you in class for more practice.